Welcome to the deep dive. Today, our mission is, well, it's a big one. We're tackling a really core concept from electromagnetism, the vector potential. The thing we always write is math BFA. And for a long time, maybe almost a century, physicists kind of treated math BFA as, well, just a mathematical trick, didn't they? A way to calculate the magnetic field math BFBA, which seemed like the real thing. But it turns out Math BFA isn't just a background player. Our deep dive today really gets into this question. What's fundamental? Is it the Math BFB field we measure, or is it this potential Math BFA, especially when we look at energy or, quantum mechanics?
Exactly. And the way we get into this, maybe surprisingly, is by looking at something practical. How much energy is stored in magnetic fields? We find our first intuition about energy, well, it kind of breaks down for steady currents. And that breakdown immediately forces us to bring in Math BFA. It becomes the essential tool just to get the energy accounting right.
Yeah.
Okay, so let's unpack this a bit.
Right. So following the source material, let's start with the basics. The magnetic dipole. We know a little loop of current acts like a tiny magnet, right? A dipole. And its strength is given by the magnetic moment, bold symbol. That's just the current dollar times the area vector of the loop, Math BFV. Simple enough?
Yeah, and if you put that loop in a magnetic field, a uniform Math BFV field, it feels a torque, a twist, bold symbol times Math BFV. It wants to line up with the field. Now, the energy associated with rotating it against that torque, that's what we typically call the mechanical energy, 1 Mach. And classically, that's minus bold symbol Math BFB.
Okay, 1 Math, bold symbol Math. And that definition works perfectly for finding forces, right? Like if the Math BFE field isn't uniform, you take the derivative of that energy and boom, you get the translational force on the loop. Standard stuff.
Standard stuff for forces, yes. But here's the twist, the really crucial distinction. That UMAC, the minus a bold symbol, Math BFB, it's not the total energy in the system, electromagnetically speaking.
Wait, not the total energy. Why not? It's the work done, isn't it?
It's the work done on the loop itself. But think about it. We're dealing with steady currents. That means something, like a battery, is working hard to keep the current I$ constant, even as the loop moves or rotates in the magnetic field.
Ah, okay. So if the loop moves through the field, there's an induced EMF, like Faraday's law.
Exactly. There's an induced EMF, a back EMF, because the flux through the loop is changing as it moves or turns.
Right.
To fight that EMF and keep the current steady, the external power source has to push charge against it. It has to supply energy. And it turns out the amount of energy the source puts in is actually twice the mechanical work calculated from the force. It's a bit counterintuitive, but necessary for energy conservation.
Twice the work. Wow.
So when you add the energy supplied by the source to the mechanical work done, the total electromagnetic energy of the system, one total ends up being the negative of that mechanical energy. So we total is actually plus bold symbol Math BFB.
The sign flips. One total plus bold symbol Math BFB, that's a huge deal. It means our simple mechanical definition just doesn't cut it for the total energy picture when currents are kept steady.
Precisely. It's a clear signal we need something more general.
Okay, so if bold symbol Math BFB is wrong for total energy, how do we find the right total energy for any old arrangement of steady currents, not just these tiny dipoles?
And that is where the vector potential, Math BFA by, really enters the stage in a fundamental way. We can imagine any circuit, any current distribution, Math BFJ, as being made up of loads of tiny current loops. When you sum all that up, using Math BSJ, the total energy stored in the magnetic field due to these steady currents comes out beautifully as $1 Math BFJ, DFJ VV.
1/2 integral of Math BFJ over volume?
Exactly. And if you look at electrostatics, the energy is 1/2 integral of charge density times the scalar potential ignoral day. So this magnetic energy formula, it's the perfect analogy. Math BFA plays the role for currents, that BFA plays for charges in terms of energy.
Okay, so Math BFA is essential for getting the energy right. But this leads us straight into that big conceptual headache for classical physics. The whole Math BFB doll versus Math BFA thing. Math BFB day is what we measure, the force field. Math BFA is, well, it's defined by the fact that its curl gives you Math BFB or day, right? Nath BFA, Nak the Bay Dom, times Math BFA.
The core issue was its arbitrariness, or what physicists call gauge choice or gauge freedom. The thing is, Math BFA isn't uniquely defined for a given Math BFB field.
Meaning there's more than one possible Math BFA that gives the same Math BFB die.
Infinitely many, actually. You can take any vector potential Math BFA that works, and then add the gradient of any scalar function you like, let's call it PC. So you add nabla PC to Math BFA. The curl of a gradient is always 0. So the curl of this new math BFA, which is math BFA plus nabla-p, is exactly the same as the curl of the old math BFA. The math BFB field doesn't change at all.
Okay, like choosing the 0 point for potential energy, you can set sea level as 0, or the floor, it doesn't change the physics of gravity.
Exactly the same idea. So classically, the argument was, if math BFE is the physical reality, the thing that exerts forces, and you can change math BFA all over the place without changing math BFB, then math BFA can't be physically real. It must just be a mathematical tool, a convenience.
Makes sense from that perspective. If it's not unique, it feels less fundamental.
Right. Useful, often easier to calculate math BFA AGE first for some current distribution and then find math BFE from it, but not considered real in the same way math BFBA was.
But then, quantum mechanics arrives. And this whole classical picture of only B matters gets completely overturned, doesn't it? Classically, if math BFB it is 0 in some region, nothing magnetic should happen there. No force. End of story.
But quantum mechanics cares about something classical physics mostly ignored.
Mm-hmm.
The phase of a particle's wave function. The probability of finding an electron, for instance, depends on this phase, and it turns out that the vector potential math BFA directly affects this quantum phase. Specifically, the change in phase along a path depends on the line integral of math BFA along that path, fits math BFA c dot on h.
So math BFA itself, not just math BFA, is influencing the quantum behavior. Okay, let's talk about that famous experiment, the Aharonov-Bohm effect. Can you describe the setup?
Sure. Imagine you have a source emitting electrons. You split the electron beam into two paths, like in a double-slit experiment. These two paths go around either side of a long, thin solenoid.
A solenoid, right? Like a coil of wire. And the key thing is, the magnetic field math BFB produced by the current in the solenoid is completely trapped inside it.
Exactly. Outside the solenoid, where the electrons are actually traveling, the math BFB field is essentially 0, or can be made arbitrarily close to 0.
So classically, the electrons shouldn't feel a thing. They're flying through a region with no magnetic field.
Classically, absolutely nothing should happen. The two electron beams should recombine and create an interference pattern, and that pattern shouldn't change whether the solenoid is on or off because math BFB won outside.
But that's not what happens, is it?
Not at all. When you turn the current on in the solenoid, even though math BFB is 0 outside, the interference pattern shifts on the detector screen.
It shifts, even with no B field where the electrons are.
Because even though math BFB is 0 outside, math BFA is not 0 outside. The line integral of math BFA around a loop enclosing the solenoid is non-zero. It's related to the total magnetic flux trapped inside the solenoid. And since the electron's phase depends on the integral of mass BFA along its path, the two paths pick up different phase shifts when the solenoid is on. That difference in phase shift causes the interference pattern to move.
Wow. So the electrons are affected by the magnetic field, but only through math BFA in a region where math BFB itself is 0. That's kind of mind-bending.
It really is. It fundamentally showed that math BFA, this supposedly arbitrary mathematical potential, has direct, measurable physical consequences in quantum mechanics. It forces you to reconsider what's truly fundamental. Is it math BFB or is it math BFA?
The thing we thought was just a calculation trick turns out to be essential for describing quantum reality.
Okay, that's a huge point. Now let's shift gears a bit. We've been mostly in the realm of statics, steady currents, constant fields. What happens when things start changing, when we move into dynamics? How do math BFA and untidily fit in there?
Right. Dynamics is where things get more complicated, but also more unified. The main thing is that influences can't travel instantly. Information about changes in fields propagates at the speed of light. This means some laws that worked perfectly well for statics just aren't true anymore. Coulomb's law, for instance, assumes the force depends instantaneously on charge positions. That's only an approximation.
And the idea that the electric field math BFE always has 0 curl, that goes out the window too, right?
Absolutely. In dynamics, Faraday's law kicks in. Partial math BFE partial T dollar. A changing magnetic field creates a curling electric field. That's fundamental to light waves, for example. So the static laws break down. How do the potentials defined in Math BFA Day help us describe these changing fields?
They become even more essential, and they get linked together. You can't just calculate math BWALPhi anymore, or math BFE Day from math BFE independently in the simple static way. Instead, the full Maxwell's equations in terms of potentials show that math BFE depends on both the gradient of Phi and the time derivative of math BFA tal. And math BFB still comes from the curl of math BFA.
And these potentials now have to account for the travel time, the speed of light delay.
Precisely. We talk about retarded potentials. The potential total VFE at a point in space and time depends on the charge density at other points, but at an earlier time, the time it took for the influence to travel. Same for math BFE depending on the current density, math BFJ, at earlier times.
So phi alpha j and become the carriers of the electromagnetic interaction, respecting the cosmic speed limit. You really can't do dynamics without them.
Not if you want a complete consistent picture. They combine beautifully, actually, into a four-vector in relativity, showing how deeply connected electricity and magnetism are in spacetime. But yeah, math BFAs is absolutely central.
Okay, so let's try to sum this up. We went on quite a journey. We started looking at the energy of just a simple current loop.
Uh-huh. And found that simple mechanical energy 1 math BFB wasn't the full story for steady currents. The total energy is actually 1 total plus bold symbol math BFD.
Right. And getting that total energy generally required introducing the vector potential math BFA, leading to the formula $1 math BFA TAs A of E.
Then we hit the classical problem. Math BFA isn't unique. You have this gauge freedom. So what was seen is just a mathematical tool.
Until quantum mechanics and the Aharonov-Bohm effect showed that math BFA directly affects the phase of an electron's wave function, producing real, measurable effects, even where the magnetic field math BFB is zero.
Yeah, that was the kicker. It strongly suggests math BFA, despite its arbitrariness, is physically significant, maybe even more fundamental than math BFB at the quantum level.
It really reshapes how we think about fields and potentials. Okay, so here's a final thought to leave everyone with, something to mull over. We have this vector potential math BFA. It dictates a real physical effect, that quantum phase shift. Yet, we also have this mathematical freedom, this gauge choice, to change math BFA by adding the gradient of some function, nabla PC, without changing the measurable math BFB field. So if we can freely choose aspects of math BFA, but math BFA has direct physical consequences, what does that really mean? Does the physics depend on something we can just choose? Or is there some deeper layer to gauge freedom and the nature of math BFA that we still haven't fully grasped? Something to think about.